Hey, welcome back to Chapter 9. This is sections D and E. Let's jump into parallel and perpendicular lines. Parallel lines are simple enough. If two lines are known to be parallel, then that means that they have equal gradient. Their slopes are the same. And that also works in the opposite direction, which probably seems obvious. If two lines have the same gradient, then we can say that they are parallel. All right, so parallel is simple enough. We're just looking to have the exact same slope. Perpendicular lines are a little bit more complicated. So first of all, we're talking about lines which are not horizontal or vertical, and I'll explain why that is in just a moment. But for all other lines, if we know that they are perpendicular, then that means that their gradients are negative reciprocals. And if the gradients are negative reciprocals, then that means that the lines are perpendicular. So this phrase, negative reciprocals, sounds a lot more complicated than equal. So let's look at that, and then that will explain why we're not talking about horizontal and vertical lines here. So here are two examples. So if our first line has a gradient of 2/7, then a perpendicular line to it is going to have a gradient which is the negative reciprocal. So it's going to be negative, and then the reciprocal of 2/7 is 7/2. So that's the negative reciprocal of 2/7. And if our original gradient was -5, we're going to consider that to be a fraction, so -5 divided by 1, therefore its negative reciprocal is going to be 1/5. So why did our definition on the previous page specifically exclude horizontal and vertical lines? Well, horizontal and vertical lines are clearly perpendicular, don't get me wrong, but we know from the previous video that the slope of a horizontal line is exactly 0. So when we take the reciprocal of that, and this could be like 0 over whatever number we want, as long as it's not 0. So let's say it was 0 over 4. So here's two points that are 4 units apart. When we take the reciprocal of that, then we're going to have -4 over 0, and that's not allowed. That's not defined because we can't divide by that 0. So that's why this rule doesn't really apply to those. But again, certainly horizontal and vertical lines are perpendicular. It's just that we wouldn't think about this whole negative reciprocal thing with those. All right, for now, that's all I have to say about parallel and perpendicular lines. It's going to come back later in the video, so don't forget about it. But now we're going to move on to something else, just a bit of vocabulary, which is to say that points are considered to be collinear if they lie on the same straight line. You can kind of see that in the word there, collinear, so they're sharing a line. In our image here, A, B, and C are all collinear because they're on the same line. They're on the line L. Therefore, since they're on the same line, the slope between A and B is exactly the same as the slope between B and C, which is also, I should point out, the exact same thing as the slope between A and C. All of those have to be the same. Now, in this case, it was obvious because we saw in the picture that they were all on the same line. But we can also prove algebraically that 3 points are collinear if, when we calculate the gradients, they end up being the same. I want to point out, though, that we need to share some letters. So we see down here in the blue box, A, B, and C are collinear if the gradient of A, B is equal to the gradient of B, C. And I'm putting a lot of emphasis on that B there because say I had a parallelogram and I were to prove that the gradient of AB is the same as the gradient for CD. That does not mean that A, B, and C and D are collinear. Clearly they're on different lines. For points to be collinear, they have to have the same slope and they have to definitely be on the same line. How do I know that these points are on the same line? Well, it's because we're using the point B in both cases. Clearly, in the picture I've drawn, the gradient for AB is not going to be the same as BC, so we wouldn't be fooled into thinking that they were collinear if we were to calculate it here. But we can't just choose any random points and decide that they're collinear because they have the same slope. All right, we need to share one point. So here's an example of how we could do that. Again, it's just putting stuff into the gradient formula from the previous video. they chose AB here, and then they did BC here. They got the same answer, so therefore they're collinear. But they could have also done AC, and you'll get the same slope there. So which two pairs of points you want to pick, it doesn't matter. Now we're into section E. This is the more exciting section, the equations of lines. So the equation of a line is a rule which connects the x and y coordinates of all points on the line. In other words, if I know the x coordinate of a point, I can put it into the rule to get the y coordinate. And if I know the y coordinate, I can put it into the rule to get the x coordinate. There are going to be three different ways that we might express the equation of a line. So first up, we've got general form. The book calls it general. I like calling it standard form. Whatever. It's ax plus by equals c, where a, b, and c are just real numbers. And the truth about standard form is it's very, very helpful, but you probably won't appreciate why it's so helpful until you study three-dimensional vector geometry in a couple of years, maybe. Chances are you'll forget that I told you it was cool and really helpful by the time you get there, and then you'll be confused and you'll pretend that you've never seen things like this before. But trust me, it's really helpful to think about in a couple of years. For the purposes of our course, I actually find general form to be usually not the most helpful or the most intuitive form, but whatever, it works. There's nothing wrong or bad about it. Next, we have gradient intercept or slope intercept form, which is probably the one you're most familiar with, where this number m represents the gradient and this letter c represents the y-intercept. Many of you coming from an American educational background probably learned this as mx plus b. It's the same thing. Our book just uses a c instead of a b, so that's what I typed here. Gradient intercept form is really nice because I can tell immediately by looking at it what is the slope of the line and what is its y-intercept. And for our purposes dealing with just two-dimensional flat plane geometry, that's really nice. That's super, super helpful. I have to think a little bit harder when I see an equation in general form to work out what should this line look like. So for us, gradient intercept is amazing. But equally amazing is the last one, point slope form. So in this one, this m is the exact same as the m in the previous one, so that just represents the slope. And what we've got is we still have an x and a y, which are just variables in the equation, same as in the previous two examples, by the way. The x and y were always going to be letters. And then we have x1 and y1. We saw that in the previous video. Those are going to be the coordinates of a single point on the line. There's a connection between gradient intercept form and point slope form, or I guess you could call it point gradient form, by the way. They both tell us immediately what the gradient is, and they both also tell us a single point on the line. Slope intercept form tells us specifically the y-intercept, whereas point slope form just tells us some random point, which might be the y-intercept. In fact, if you think about it, the y-intercept of a graph is exactly where x equals 0. Therefore, this x1 would be equal to 0 if we were using the y-intercept in point slope form. So then if we added y1 over to the right-hand side, we would get y equals mx plus y1, and that would just be slope intercept form, but derived from point slope form. Okay, point slope form I never appreciated when I was in high school until I got to calculus. When I got to calculus, I realized how helpful this form was. I'm going to really encourage you to embrace point slope form even if you're more used to dealing with slope intercept form. In fact, you're going to see in the examples on the next couple of screens the first steps that the book uses is often point slope form, and then from there they change it into some other form. And I think that's unnecessary. I think point slope is totally valid. In the next couple of examples, we'll see also that the questions are going to ask for a particular form for the answer. And that's not something that I am particularly interested in. However, we'll look at it. You might find on like an SAT or something like that, that the question forces you to write your answer in a particular form, but that will not be a focus for my course. The thing that we need to be careful about with point slope form is these minuses. So that means that if our point happened to be, let's just say 3, -5, this bracket would read x minus 3, and over on the left, we'd have y plus 5. So we just need to remember that, well, it's not that the sign is changing, we're just subtracting away the coordinates in each case. Some people like to think of it as change the sign, the -5 becomes positive, the 3 becomes negative. I don't like to say that, but anyway. In order to find the equation of a line, we're going to need some amount of information, and that'll be either the gradient and one additional point on the line, or 2 points on the line. Why is this okay? Well, because if we know 2 points, then we can figure out what the gradient is using the formula from the previous video, and then we have the gradient and at least 1 point lying on the line. Okay, so in this example, we're asked to find our answer in gradient-intercept form. We're told the gradient is 5 and it passes through the point -1, 3. So the first step the book uses is point slope form. We're doing y minus this y coordinate, so that's y minus 3, equals the slope times x minus that x coordinate, so x minus -1. Minus a negative is a positive. We get this. To me, that's a perfect answer. That's the equation of the line in point slope form. I love it. The book wanted gradient intercept. That's fine. We distribute the 5, and then we add the 3 over. This tells me the gradient is 5, and the y-intercept is 8. We could also write this in standard form. That would be 5x minus y equals -8. No big deal. We should be able to transfer between these 3 forms without too much difficulty. Here's another example. They want general form this time. Again, we're told the gradient is 3/4, and it passes through the point 5, -2. So point slope form, y minus -2 equals 3/4 times x minus 5. If it were me, I'd pretty much stop right there. In the book's answer, they immediately multiplied by this 4 to get rid of the fraction, but if you'd prefer to distribute the 3/4, then you'd get work looking like what I wrote down over on the right. And you should eventually be able to get here. And then if you just multiply both sides of that equation by 4, we get exactly this. Usually standard form is given with integer coefficients of x and y, so that would be the proper general form. But in practice, what I wrote here is good enough. Again, I'm thinking ahead into why standard form is important in higher dimensional geometry, but you don't care, right? Okay, here's another one. Gradient intercept form is what they want. We're only told 2 points that the line goes through. So first thing we're going to do is calculate the slope. We do 5 minus 3 over -2 minus 1. We could have also done 3 minus 5 over 1 minus -2. We're going to get the exact same thing. Our slope is -2/3. That's going to go into our point slope form. And again, I'm done here. That's a perfectly correct answer. The book insists on doing gradient intercept, so they distribute the -2/3 and add the 3 over. As our friend in the corner points out, we could use either of the original 2 points to get to our final answer. So in green, I've used -2/5 as my second point, and I get the same thing. What that means, though, is that these 2 lines, so the one I've just circled in red and the one I had circled in blue before, They're both in point slope form. They're both the exact same line. They look kind of different because they have, one has y minus 3, the other is y minus 5, one has x minus 1, the other is x plus 2, but they are the exact same line. If you choose any x value and put it in here and here, you're going to get the exact same y value out. So the nice thing, I suppose, about slope-intercept form or standard form when you have integer coefficients is that there's only going to be one possible way that their answer could look, whereas with point slope, you've got an infinite amount of points on a line really to choose from, so there's lots of different ways that your answer could look and can still be correct. Now I'm going to look at a few more examples. I'm not going to do all of these, but I just want us to, I'm going to do the first few steps of each one. The remaining steps would have been just like the examples we just saw. I want to look at these because these each have an added element of vocabulary that we need to think about. So in this first example, letter A, we're told that the line cuts the x-axis. What does that mean? That means that the line is going to go through the x-axis at 5. In other words, it passes through the point 5, 0. And it cuts the y-axis at -2. That means it goes through the point 0, -2. So now I have 2 points. I can find the slope between those 2 points and then choose either one of them to work out the equation on my line. In the second example, B, it cuts the x-axis at -1. So again, that's -1, 0. We're told the second point. So we have 2 points. We find the slope. Move on. Letter C, it's parallel to a line with a gradient 2. Remember parallel lines from earlier in this video. If the lines are parallel, that means that they have the exact same slope. So we know the slope is 2, and we know it goes through this point. So we can go into point slope form. We're good to go. Letter D, it's perpendicular to a line with a gradient of 3/4. That means our gradient is going to be -4/3. Cutting the x-axis at 5 means it goes through the point 5, 0. So we've got a point, and then we've got the slope. If it's perpendicular to a line with a gradient of -2, that means the gradient we want is going to be +1/2. And again, we have a point. So it's really important that we be able to translate between words and the equation of a line. More on that in just a minute. Just wanted to share now, the book gives some shortcuts for dealing with the general form of a line. I think many of you watching this probably aren't going to want to allocate too much of your mental energy to this shortcut. I don't think it's worth that much. It doesn't save a whole lot of time, but I'll talk about it for just a moment. If we know that the equation has a gradient of a over b, then its general form is going to look like this. It's going to be ax minus by equals c. And that should be obvious if you think about writing it in slope-intercept form. We're going to have to bring the by term over to the other side, and then dividing by b. So we'd have positive a divided by positive b as our slope. And likewise, if our equation was negative a over b, then we're going to have ax plus by equaling c. Now what is c? Because the a and the b are coming directly from the slope. Well, that c term is found by substituting any point that we know is on the line into our ax plus by. And this is the part that you'll never remember that I said, but it connects really, really well to higher dimensional geometry. I'll show you what I mean. So if we know that a line has gradient of 3/4 and it passes through 5, -2, we're going to start off by writing 3x minus 4y. Again, that's coming directly from here. It's going to be 3 and then a -4. And then to find out what the c value is, we substitute 5 and -2 into that. So it's 3 times the x value minus 4 times the y value. And we get the value of 23. That's our c value for this equation. In the second example, we had a slope of -3/4. So we're going to write 3x plus 4y and it goes through 1, 7. So it's 3 times 1 plus 4 times 7. That equals 31. So that's our standard form. Now, if I'm just interested in writing any form of the line really quickly, I would just use point slope, because in both of these cases, I can immediately write down in the first, y plus 2 equals 3/4 times x minus 5. And in the second, y minus 7 equals negative 3/4 times x plus 1, or excuse me, minus 1. So I can write down an equation in some form super fast. I don't need this additional shortcut. This is a shortcut to work out the standard form of the line really quickly if you really wanted it. And again, it has such nice applications later on in higher dimensional geometry. In fact, you know what? Fine. Here, this is from another course that I teach, and you don't need to worry about what all this nonsense means. If a plane has a normal vector, don't worry about all that. What's important is that, well, okay, look. We have a line, that's a one-dimensional object. We've spoken previously, if we were to extend the line into the second dimension, then we would have a plane, right? It's like an x-axis and a y-axis. So this is an infinitely large two-dimensional geometrical object. What's the equation of a plane? Well, it turns out we can find it as ax plus by plus cz equals d, where what is d? It's that number a times the x-coordinate of some point on the plane, plus b times the y-coordinate of some point on the plane, plus c times the z or z coordinate of some point on the plane. And I know this is in three-dimensional space, and that's a lot right now, but I want you to appreciate the fact that this is the exact same structure as that of the standard form of a line. And maybe now you'll remember that when you see it when you're like a senior or in college or something. Okay, back to stuff we need to know. We can apply some of the concepts here again to some more interesting problems coming from the world of geometry. So we have a circle. We want the equation of the line, which is tangent to that circle at this particular point. We can visualize that. We want the equation of the red line in that picture. How are we going to do that? Well, we know a point on the line right away, -1, 5. We need either another point on the line, which, sorry, we're not going to be able to work that out, or we need the slope of that line. Well, finding the slope of that line directly isn't so obvious, but we have this other line segment here. And we know that that line segment has to be perpendicular to the line in our question, because this is a radius intersecting with the tangent. So those are always going to meet at a right angle. And we can work out the slope of CP, since we know both of its endpoints. Therefore, the slope of our line, being perpendicular to that, needs to be the negative reciprocal, 3/2. And so we can come up with the equation of the line in any form we want. This particular answer is given in standard form. To repeat myself, once again, I would have used point slope form, and so should you. To conclude, I mentioned a few moments ago that it's really important that we be able to translate between words and the equation of a line. However, I want to extend that to say it's really important that we be able to translate between all four of the multiple representations of any type of function. So far, we've only really looked now at linear functions in depth. Later on, we'll see quadratics, exponentials, and trig functions. And then there's plenty more for you to work with in other courses. But every function can be thought of in 4 different ways. We could describe a function as an equation or a rule. We can describe a function as a graph. We can describe a function as a table of values. Some of you might call that like a t-chart. You know, it's just where you have a bunch of x and y coordinates listed out. And then we could describe a function as a pattern or as a few sentences of information or as about some complicated word problem. That one's kind of vague, but it's important that we be able to connect between all four of these because they all describe the same thing. So when I say the word line, you might just picture the graph of a line, or you might picture the equation of a line, or you might picture a table of values that looks like a line, or you might think of, I don't know, something that changes linearly. I'll show you what I mean with one example. Here's an equation in red, a table in blue, a graph in black, and a weird pattern of growing squares in green. But all four of these are a single representation of the exact same line. With a little bit of thought, you should be able to change in between any two of these. You can see immediately how the points on the graph, for example, are also points on the table. You can see how points on the table are actually counting up how many squares there are in each of these pictures. In the first picture, there's 1 square. In the second picture, there's 5. In the third, there's 9, and so on. And we can see how we could get the equation from the graph because we can find the slope and we see the y-intercept. But we can also get the equation from the table by noting that as x grows by 1, the y value always grows by 4. That gives us a slope of 4. And then we could choose any of the points to work out the point slope form. Or we could work backwards in our table to work out that when x is 0, y has to be 1 minus 4. And that green pattern down at the bottom, again, here I drew a weird picture, but that could have also been a word problem describing some situation which starts at -3. I would consider that to be the starting value of our situation because it's when x is equal to 0. It's the first point on the line when we consider only non-negative x's. And that situation could grow in such a way that whenever the x value or some quantity in a real world situation, but whenever that grows by 1, the y value would grow by 4. Could be anything. But don't worry, we're going to have plenty of opportunities to play around with this stuff. Since we're only talking about linear functions, it's not really that difficult in the big scheme of things, but there certainly is going to be some element of problem solving and creativity required to deal with them. That's all for today's video. In the next one, we are going to finish off Chapter 9 with perpendicular bisectors. I'm really excited about it because that topic has this really cool application that is, it's just really neat, and I'm excited to do it with you. But you'll have to wait until next time.